Now let us start the study for waveguides. So suppose that you have any shape, and as I said in the first hour, the waves will be reflect from the boundaries of the metallic boundaries. Inside the waveguide you have some material which has electric permittivity and magnetic permeability, and generally it propagates one direction, and that direction we will take, let's say, Z. Z will be the longitudinal direction of the waves on the average they propagate. And you have transverse direction xy. So let us introduce the Maxwell's equations again. Del cross E plus del B over del T is equal to 0. Since the waves are oscillating, let's say that the one harmonic frequency omega, then that will be written as curl of E minus I omega B. The modified Ampere's law, curl of H, source of the magnetic field is the current density plus the time rate of change of the electric displacement. And here we will take the current density 0. That means that in the waveguide no free current density. Okay, so if you say this is the waveguide, inside there's some material but no free current density. So there's some electric displacement, all sorts of things there, but no current density and no charge density also. Then that takes the form of curl of B. You can write B and H using the magnetic permeability, and that will be equal to minus mu frequency E and epsilon also. So H is you can write the H in terms of B over mu, mu goes there, and D is epsilon E, and del over del T is minus I omega, you get that. The other conditions, del dot B is equal to 0 and del dot E is equal to 0. No charge density and no current density in the waveguide. Let us quickly combine this and write the wave equations as we did earlier. So curl of E is equal to I omega curl of B, and curl of E is gradient of divergence of E minus Laplacian E I omega, and instead of curl of B you can write minus I mu epsilon frequency times the electric field, no free charges, del dot E equal to 0, and you will obtain Laplacian E plus mu epsilon frequency square E is equal to 0. So this is the wave equation. In free medium the solutions are the plane waves. If the sign is okay, this is minus, plus goes there, everything is minus, everything is okay. So if you do the same thing for the magnetic field, you will get the wave equation for the magnetic field. So now we will look at the solution not for infinite medium, we will look at the solution for a bounded for walls. So the waves are bounded by the wall, so it is reflecting back and forward and going on as a transmitted. So we will decompose the things into two quantities. One, what you have here, Laplacian. You can decompose the Laplacian into two pieces. One will be the Laplacian for the transverse, that is nothing but del square over del x square plus del square plus del y square. The other is del over del z square. Okay, we will try to decompose everything, Maxwell's equations, in the transverse and longitudinal direction. Okay, two of them scalar and two of them vectorial. So we will study the transverse and longitudinal forms of the Maxwell's equations. And the wave equation could be written in that form in the following. So both of them could be written in the following. So we have to define some particular solution. So some particular solution is in the following. Our electric fields and induction has dependence on x, y, z and time. X, y, z and time. For the z direction, propagation direction, we will take the terms of the plane waves. So plus minus kz minus I omega t. Plus minus kz I omega t. But for the transverse components, we don't know what are they. Some dependence E in terms of xy and some dependence of B vector in terms of xy. So this is the form of the solution we will take, except. So in propagation direction, we have some sort of plane waves, but in transverse, we don't know the form. So depending on the geometry, we have to define the fields. We have to find the fields. So if we have this kind of solution for the wave equation, they takes the following form. So for example, for that one, take the Laplacian as Laplacian of transverse. T represents the transverse plus del square over del z square plus mu epsilon frequency square, and substitute one of those or both of them, e xy e to the plus minus kz minus I omega t, b xy e to the plus minus kz minus I omega t. So automatically you will see that this del over del square over del z square takes what? Ik plus or minus, it doesn't matter. That becomes what? Minus what? K square. Okay? So if you add this, one of the solution, okay, this doesn't have z dependence. So if you decompose the Maxwell's equations and the wave equations, first things for the wave equation, you will have the following format. Del square t plus mu epsilon omega square minus k square and then you have EXY and BXY and the exponential terms also, e to the plus minus kz minus I omega t, e to the plus minus kz minus I omega t have to be equal to 0. First thing, this is simple. We have the wave equation, we have the Laplacian in terms of transverse and longitudinal. You convert the wave equation to the transverse. So this is a Laplacian in the transverse. This is a plus del square over del z square. If we add this will be c only the z, and it brings ik plus minus ik, and altogether that will be minus k square. So this is coming from here, or in other words, you can write del square over del z square, replace my minus k square. Okay? Is it okay for everyone? So it's trivial. Now, how many equations we have? 3 for electric field, 3 for B, 6 equations, 6 wave equations. Okay? We don't want to solve 6 wave equations. So the idea is the following. We will find the solution for the Z component, E or B, and we will show you that the other transverse component, XY, transverse components of the electric and magnetic fields are related with the Z component. Okay, so this is our way. So you have to wait and see what is going to be. So first, let us try to decompose the Maxwell's equations in terms of longitudinal and transverse components. So one of them is very simple, del dot B. Del dot B is equal to 0. How we can write this? Gradient could be written as transverse component plus del over del z, let's say k, dot product B transverse plus BZK. This and this are the same. So first one is the gradient in the transverse plus del over del z k. This is the gradient. And divergence of B is B transverse plus BZU, right? And what is this? That is equal to del transverse dot B transverse. This is the first term, divergence of this. If you look at this and that, what you are going to obtain? What are the directions of the 0? This is xy direction, this is along z direction, 0. What are these? Dot product. This is k direction, this is B transverse. 0. B transverse is along xy direction, that is 0. And this is left. Del over del z, Bz equal to 0. So this is one of the Maxwell's equations related to there's no magnetic monopoles. You can write in that form. And similarly, what will be the del dot? So let us keep this. What is del dot E equal to 0? So that is equal to what? Divergence of the transverse, E transverse plus del over del z, Ez have to be equal to 0. Okay, in the same way. So B transverse means that we have Bx, I, By, J, and gradient transverse means that del over del x I del over del y j. So del dot b is a scalar equation, del dot e is a scalar equation, and we have two equations. Both contains the transverse and longitudinal informations. But the other equations are a little bit tricky. So I am going to erase this middle, but let me write first the wave equation here quickly. Laplacian of transverse mu epsilon frequency minus k square, and you have some general E or B, three-dimensional, have to be 0. Now let us start to play with the vectorial forms of the Maxwell's equations. I'll start with the Faraday's equation. Curl of E is equal to I omega B. So first thing I am going to look at this is a vectorial equation. Basically that vectorial equation has three components, but what I needed here, longitudinal and transverse. How can I obtain the longitudinal component of this equation, Faraday's equation? You have two options. You will either do a dot product with the z or cross product. Which one you choose? This is a vector equation, and I want to look at this along the z direction. What you are going to do? If you take the dot product with the z or k, that will be the longitudinal. If you take the cross product with the what? Z, that will be transverse. So let me take the dot product with the z-axis. So let us write the things. You can write this gradient as gradient of the transverse plus del over del z k hat. Cross product E, you can write the E as a E transverse plus Ez k hat, and plus that is equal to I omega B transverse Bz k hat. Okay. Then take the dot product with the k hat, both sides. Which term will survive on the right hand side? B transverse dot k. What is the B transverse dot k? 0. This will be survive on the right hand side. So for the right hand side, you have I omega Bz. For the left hand side, what we have? First term, k dot curl of E transverse. And what are the other terms? This and that curl, that is equal to curl of the transverse Ez k hat. And what is this? So that you can write this as a k cross E transverse. So say that del over del z k cross E transverse. And this one, what is this? What is this? This is along K. This is along K. K cross K. K cross K.
Cross K.
K cross K. K cross K. Okay, this is something with K cross K. That is 0. So this last term will be 0. So what will be, which terms will be survive here? For example, this will be I, J, K, and del over del x, del over del y, z is 0, and 0, 0 is z. So what is that term? This is the, what? Curl of Ez, so transverse component of the gradient cross product Ez. Okay, so which terms will be survive? I will be survive because this, and what else? J will be survive. So this all together will be along which direction? No, all together. What will be the direction? In xy plane, ij, and scalar product with k will be what? 0. And if you look at this one, what you are going to obtain? So you have the same structure here, I, j, k, and 0, 0, del over del z, ex, ey, 0. Which term component will be survive? I component will be survive, J component will be survive, but the Z component will be 0. So this is along, again along xy direction, and the scalar product with x with Z will be 0. So these two on that will not contribute, and what I am going to obtain, maybe I should write here. Maybe I should write here, that will be what? K dot product curl of the transverse with E transverse have to be equal to I omega bz. This is the form of the Faraday equation in longitudinal direction. Okay. Which equation similar to the Faraday's equation in here? Look at the symmetry of these two. More simple, you can see. Can you see a symmetry between the Faraday's equation and the modified Ampere's law? What is changed between these two? Instead of E, that goes to B. And here, what happens? E and B replaced, but the coefficient is replaced by a factor of what? I mu. So if I want to write that, if I do the same thing for the other one, what I should write? So let me write this as a I omega B. If I want to take that the longitudinal component of the Ampere's law, what can I write? So if I do the same thing, algebra here, what I am going to obtain? So what will be the Z component of the modified Ampere's law? This is the Faraday's law in longitudinal. So what I am going to obtain for the modified Ampere's law? So instead of E, so look at the symmetry between these two equations. What is the symmetry? E is replaced by B, and E is replaced by B, and the coefficient is replaced by what? I omega is replaced by minus I mu epsilon omega. So could you tell me what I am going to obtain if I do the same thing to the other? What will be the longitudinal component of the Faraday's equation? So E transverse will be what? B transverse. BZ will be Z, and I omega B will be what? Minus. Yes. So if you do the same thing, you will get the same. If you do the same algebra, you will get the similar structure. So you will get K dot curl of the transverse of the B transverse minus I mu epsilon frequency Ez. So this is the second one, is the modified Ampere's law along the longitudinal direction. Now let us look at the transverse directions. What we have for the transverse direction. Again, pick up the Friedreich equation. Curl of E is equal to I omega B. This is the Friedreich equation. And take the, in order to find the transverse component, what we have to do now? In the previous examples, we did the scalar product along the z-axis. Now what we have to do? How you can find that the transverse equation, transverse components? Cross product with z, automatically. So this is a vector. So you can look at the projection along the z, and you can look at the perpendicular to the z. So we have tools, scalar product and cross product. So let me take the cross product of this with K. K cross K cross. For the left hand side, let us start. K cross curl of E. So I'll write the curl in open form. Del over del Y Ez, del over del Z Ey I. So you know that this I J K del over del X del over del Y del over del Z Ex Ey Ez. So this was the I component. The second one for the J component. For the J component, del over del X Ez minus del over del Z Ex. This is for J component, and some terms for the K component. That is equal to what? For the right hand side, what you have? K I omega K cross B. B is B transverse plus BZK. And close this one. So if I take the cross product with the K, with that term will be what? 0. So K cross K will be 0. And for that one, if I take the cross product, which term will be the 0? Which term will be 0? Second term, K cross K will be 0, and you will get I omega K cross B transverse on the right hand side. And for the, go to the left hand side, what is the K cross I? What is K cross I? J or minus J? J. And how is this one? This one? K cross J? Minus I. So use the cyclic rules. So let me go one more step. For that one, you will have del over del y Ez minus del over del z Ey along J. You have minus and minus, that becomes plus del Ez over del x minus del Ex over del z I. So here you can do the following thing. So look at the del over del z. You have here and you have here. If you take the parenthesis of minus del over del z, what you are going to obtain? You have two terms of del over del z with minus. If you take the minus del over del z, you will have what? So Ex I Ey J. And what is this? E transverse. Ex plus Ey. Okay? E transverse. Transverse electric field. And what are the other terms? Look at here, what you have. What is left over? You have I del over del x, del over del x I for this term, and you have what? Plus del over del y j acting on what? Acting on Ez. And right hand side is I omega k cross b transverse. Do you agree this one? Look at this, del over del x I, del over del y j. And what is this? What is this? Del over del x I plus del over del y j. So that is a gradient operator in transverse direction. Okay? So you have to go over these lecture notes by yourself, so they are not difficult. So altogether, this equation takes the following form. This equation takes the following form. Del over del z E transverse, take this to the other side, plus I omega k cross B transverse, I take this to the other side as positive, is equal to gradient of the transverse of Ez component. So, any problem here? Okay? Okay. If you want to write the same thing for the modified Ampere's law, what you are going to write? Again, same. How the fields are changing between the Ampere's law and the Faraday's law, modified Ampere's and Faraday's law. E and B replacing and this coefficient is replaced by a factor of minus. So basically, if you do the same thing for the other one, you will get del over del z B transverse. What will be the I omega? What you are going to write instead of I omega? Minus I, yes, right, you are right. So that will be minus I mu epsilon omega k cross E transverse is equal to gradient of the transverse Bz. This is the summary of the Maxwell's equations. Two scalar equations, and you have actually 6 equations in component wise, Faraday's law and the modified Ampere's law, but you decompose these equations in longitudinal and transverse. Okay. Now we are coming to the end of today. I am going to show you that this Maxwell's equations, or that one, gives the information of the following. Transverse components could be written in terms of the z components, and the z component could be calculated using the wave equation. That is the idea. Now let me show what I am going to do. So, how the z components are behaving? How the z components are behaving? When we start the wave, we said that E or B has what? X, Y dependence, sorry, and the z dependence are in that form. Okay. So can B could be written as B transverse plus BZ? Yes. Can E could be written as E transverse plus EZ? Yes. How is the Z dependences? It's like a plane waves. Therefore, what can I write instead of del over del Z? What can I write instead of del over del Z? You have del over del Z here. If you put the solution, you have the exponential term as e to the plus minus kz. Derivative of this with respect to z is what? Ik. So you can replace that the del over del z with ik. Del over del z with ik. You know that del over del t is replaced minus I omega for the exponential solutions. So replace this by ik, or plus or minus, it doesn't matter. Plus refers to one direction of propagation, minus refers to another direction of the propagation of the waves in the waveguides, plus z or minus z. So I'll take the one of them, let's say plus, not to confuse the things much. Now, how do I solve this for the transverse components? So instead of del over del z, I write ik. And let me say this is the first equation. This is the second equation. what happened if you take the cross product, the first equation with the k unit vector. So I'll do this, you will see. Take the first one and take the cross product with k. So you will get ik k cross E transverse plus I omega k cross B transverse and k cross gradient of the transverse of Ez. This is gradient of the transverse, that is Ez. What is the middle term? A cross B cross C. What is this? That is equal to K dot B transverse along K minus K dot K along B transverse. What is K dot B transverse? 0. K transverse actually Z component, that is 0. Good. And this is 1. So basically, all middle term is equal to what? Minus I omega B transverse. Okay? So B transverse is alone. Look at the second equation here. Is there a B transverse alone? Yes. What else you have? K cross E transverse. Do you have K cross E transverse? Yes. Can you solve these equations? Eliminate the K cross E transverse. I am not going to do this, but what you are going to find? Let me say that, find B transverse with very little algebra as I over mu epsilon omega square minus K square K gradient of the transverse Bz plus mu epsilon omega K cross gradient of the transverse of Ez. So this will be the end of today. So use these two equations. You have B transverse, eliminate the K cross E transverse and find that result. What result is this? B transverse could be written in terms of Bz and Ez. Once you know that the Bz or Ez, you can calculate the B transverse. Similarly, if you find that the E transverse, if you want to calculate the E transverse, you will get I over mu epsilon omega square K square K gradient of the transverse of Ez minus omega K cross gradient of the transverse. Same structure. So the idea is the following. We have the wave equation, 6 equation. But for waveguide, we know one thing. If I solve only Z component, equation, I can calculate the transverse. Because the transverse components are related with the z components. So next time we will do practical application. We are not going to put so much detail. So this is an engineering program, but at the same time it's a very, very nice application of the multiple applications. Next time we will do applications. So far, we find that the transverse fields in